I'm Jeroen van Meij, and welcome to my lecture series on computer and network security. In this second video on secure network protocols, I will talk about transport layer security, referred to both as secure socket layer or SSL and transport layer security or TLS. And let's take a brief look at the history of SSL and TLS. It started in 1995. When SSL version 2.0 was publicly released by Netscape. Netscape was a company that was building the Netscape web browser. Subsequently, in 1996, SSL 3.0 was released, so only 1 year later, due to vulnerabilities discovered in version 2. In 1999, 3 years later, SSL 3.0 was standardized and the name was changed to TLS or Transport Layer Security. It was standardized as an IETF RFC 2246. 7 years later, a more secure version of TLS called TLS version 1.1 was created in a new RFC document. 2 years later, another version 1.2 was created, yet again in another RFC. And finally, 2014, an attack was discovered against TLS 1.0, which is referred to as the Poodle attack. Very recently, in 2018, a new version called version 1.3 was released as RFC 8446. This new version adds some improvements that increases security, such as removing backwards compatibility for insecure cryptographic algorithms, mandating forward security, and improving the latency by reducing the number of messages that need to be exchanged during the handshake. And this, of course, allows for faster web browsing because the HTTP protocol makes use of TLS for security. TLS relies on two important concepts, a session and a connection. A session is associated with a single client-server pair. They are created using a handshake protocol and define the set of cryptographic security parameters that are used when securely communicating between this pair of hosts. Sessions are associated with multiple connections and are used to avoid expensive negotiation of new security parameters for each connection that is set up. The connections are associated with a single transport layer connection, such as a TCP session. The connection reuses the security parameters defined in the session. This includes the certificates for public keys, compression methods used, encryption algorithms, hashing algorithms, a master secret key, and so on. A connection has an associated MAC write secret, which is the key used for message authentication, the write key, which is the key used for confidentiality, initialization vectors used to initialize the algorithms, and a sequence number associated with each message exchanged over the connection. And let's take a closer look at the TLS protocol stack. The TLS protocol runs on top of the standard TCP/IP protocol layers. The main protocol of TLS is the record protocol, which provides the basic security services such as confidentiality and message integrity to higher layer protocols. Second is the handshake protocol, which negotiates the MAC algorithm, the encryption algorithm, and cryptographic keys used for a TLS session. The change cipherspec protocol is used to update security parameters based on the handshake. The alert protocol can be used to communicate warning messages or fatal alerts between client and server, and the heartbeat protocol is used to keep the connection alive by transmitting an identical payload from the client to the server and back from the server to the client. Protocols such as HTTP can be used on top of TLS to provide secure communication. In this case, it is referred to as secure HTTP or HTTPS. And let's zoom in on the different TLS protocols, starting with the record protocol, which, as I said, is used for integrity and confidentiality of exchanged data. As such, we start at the application layer with the application layer data. This data is then split into fixed size fragments or blocks. These blocks are at most 2 to the 14 bytes large. In the next step, which is an optional step, the data is compressed. Then, the message authentication code, or MAC, is added using the HMAC algorithm. The key used here is the MAC write secret. Next, the entire block, including the message authentication code, is encrypted using AES, SSS, or RC428 using the write key. Finally, the SSL record header is added to identify the packet. This one specifies the higher layer protocol that is embedded inside, the version number that is used, and the length of the compressed block. And as you can see, TLS and SSL rely on an approach referred to as MAC then encrypt. This means that first the message authentication code is added and then the data plus the message authentication code is encrypted. This contrasts alternative approaches such as encrypt then MAC, which first encrypt the data and then add the message authentication code. I have a question for you related to this, which is what is the disadvantage of the MAC then encrypt approach used by TLS compared to other approaches like encrypt then MAC? Is it computationally less efficient? Is it more vulnerable to attacks? Or C, there is no disadvantage? Feel free to pause the video and think about your answer. And let's take a look at the correct answer. The correct answer is B. It is more vulnerable to attacks. For example, the poodle attack, which I will talk about later in the next video. Second important protocol in TLS is the handshake protocol, which ensures the exchange of security parameters when setting up a session. It consists of 4 different phases. So let's take a closer look at these 4 phases. The first one is the phase 1, establishing capabilities. Here, the client and the server will exchange a nonce, random value, key material used to generate the keys, which versions of TLS and SSL they support, and which cryptographic algorithms they support for compression, encryption, and authentication of messages. Second phase is server authentication. Here, the server will authenticate itself, for example, by sending a certificate. It will use public key methods such as RSA or Diffie-Hellman to exchange public keys as well, and may request the client to also send a certificate. In the next step, third phase, client authentication, the client will authenticate itself by also sending a certificate, which may be optional depending on the approach used, and sending its own public key to the server. Moreover, it can send a verification of the certificate, which is also optional. The fourth and final phase is actually based on the change cipherspec protocol and serves as a verification. Here, the client and the server will send messages to each other encrypted and authenticated using the new negotiated algorithms and keys to verify that the keys are the same and that everything works properly. And during the handshake procedure, the client and server will exchange a pre-master secret. This pre-master secret can either be generated by the client and then sent to the server using public key cryptography, when using, for example, RSA, or can be generated by the client and server simultaneously when using Diffie-Hellman. Based on this pre-master secret, the client and server can then independently calculate the master secret. This is done using the TLS pseudo-random function, which you can see on the right. This pseudo-random function makes use of HMAC in combination with MD5 or SHA-1 to generate a variable length output by repeating the process a certain number of times until enough bytes are produced. Then, the cryptographic parameters such as the session keys, initialization vectors, MAC keys, and so on are generated using the pseudorandom function and the master secret until enough bytes are created.